Right. So for those few of you who don't know me yet, my name is Matthias Dangl. And I also want to thank all of you, those here in the room with me, but also, of course, those participating via Zoom, that you're taking the time to listen to me today. Now, when I tell you a little bit about my PhD thesis about witness-based validation of verification results with application to software model checking. Now, since this is a pretty long title, let me assist you a little bit in understanding what this is all about by giving a brief introduction to some of the concepts here, some brief definitions. So first of all, let's start in the end with software model checking. Put away the cursor here. Right. So in software model checking, we basically ask the question whether a given program models a given specification. So in this sense, we can see that software model checking is a form of formal software verification, right? So we want to know whether the program is a valid concretization of the given specification. And the other term that I want to define before I start with my talk is verification results, because I would imagine that there could be different conceptions in the room here, what I could mean when I talk about verification results. So for me, verification results are a pretty basic thing. When we look at a verifier and its information flow, here we have a verifier that gets an input, a verification task consisting of a program and a specification. And then, of course, as we saw on the slide where I explained model checking, what we want to know from the verifier is whether the program models the specification. And hence, we expect an answer, either false, the program doesn't model the specification, or true, the program does model the specification. And these simple binary answers, false or true, is what I mean when I talk about verification results. Now, of course, you will argue, and you would be correct, when you say that this depicted here is not the state of the art of software verification, fortunately. The state of the art looks a little bit different, where verifiers actually give us a little bit more information about those verification results. They produce graspable artifacts that, of course, imply the verification result. For example, if a verifier finds a bug, it might output an error path to tell us where the error is. That, of course, implies that the answer was false, or it might output a proof. So that implies that the answer was true. But that's more than a verification result, in the sense that I'm using it today in my talk and in my PhD thesis. So to motivate what I did during the time of my thesis, I want to talk a little bit to you about verification and verification technology. So many of us in participating via Zoom, but also here in the room with me, are part of the verification community, either as active participants or at least participating partially here. And what we achieved together in this whole community, in this resource community over the past decades, is that we can say we have made significant advances in this technology. We have continued to develop new and improved algorithms. And we also have developed concrete tools for software verification, many of them. And even though we have all of those achievements, I guess most of you will agree with me when I said that in practice, we have to face the fact that software verification is still not as popular as testing. And so now, of course, we could brainstorm and wonder what the reasons might be here. And I guess we might find hundreds of potential answers. Now, on my next slide, I picked 4 answers, and I picked those 4 answers because I find them particularly painful. Painful in the sense that they seem kind of unnecessary from the point of view of a researcher. I argue that in practice, verification is basically infeasible for a standard software developer out there in a company in the industry. I argue that this is the case because it's just too hard for them to do. It's too hard to choose the right tool. It's too hard to install these tools, and it's too hard to configure and choose the right techniques. And even if a software developer achieves all of those hard tasks, those difficult tasks, then they're still faced with the task of interpreting the outputs of such a software verifier. And that's even difficult from my personal experience when you know about software verification. It's unimaginable how difficult it should be for a software developer who has no prior experience at all in software verification. Now they have to sit down and spend hours and hours and hours and try to understand the outputs of a software, try to understand how there should be a bug in their program according to the verifier. And in the worst case, which is not that unlikely, they spend all of the time and in the end find out it was a false alarm. And that's extremely frustrating. So of course, we need to ask the question what we can do to improve the situation. And I have to be honest here, I cannot present any silver bullet. So I didn't solve all of those issues, but I hope I was able to make some steps into the right direction. And towards that, I basically posed 2 objectives for myself during the time of my PhD thesis. First of all, to make verification more applicable in practice, and second of all, making verification more useful in practice. And what I mean by that, first of all, what I mean by making it more applicable in practice is that we should continue this trend that I mentioned earlier. We should continue to develop new and improved algorithms. We need to make software verification more efficient and more effective in practice because resources are limited. For example, if I, as a software developer, want to use software verification in my continuous integration pipeline, I'm willing to wait a few minutes, but not 15 minutes and not hours, right? So it needs to be efficient. And it also needs to be effective because in industry, we don't have toy examples and we have complex problems which have multiple different complex properties. Whereas in research, we more often than not look at complex problems in isolation and not in combination. And so what we did during the time of my PhD thesis, or my colleagues together with me, we investigated a range of software verification algorithms. We evaluated those algorithms, tried to identify their strengths and their weaknesses. And we even built a prototype for dynamically choosing a likely suitable algorithm for the software developer. Oh, what happened here? I don't know. I pressed no button, but it's back. Okay. Right, so we even built a prototype for dynamically choosing a suitable algorithm, potentially suitable algorithm, such that we at least can help the developer with one of those difficult tasks where they basically don't have the competence to choose the algorithm themselves, and we try to help them here. Unfortunately, due to the time constraints, I won't be able to talk much about this objective today. But what I will spend my time on is the second objective of making verification more useful in practice. And what we did here is that we established a standard format for verification witnesses, and we used it for several use cases. First of all, and the most important one was already mentioned in the title of my thesis and my talk, namely witness-based result validation. But we also managed to synthesize test cases from verification witnesses, and we even proposed a prototype for integrating verification witnesses into the development process, like into a real DevOps environment, an ecosystem that developers could use to use witnesses to improve their software development. And I will focus today on in my talk on the first 2 of those points. So now you may be wondering, what is this witness that I'm talking about, in the sense that I'm using it today in my talk and in my thesis. The witness I'm talking about is, of course, the one based on the standard format that we established. And in the figure here, you see only a slight change towards the figure that we had earlier with the verification result artifacts. We simply name them violation witness, where previously we had some custom error path, and correctness witness, where previously we saw this proof. So we just have a standard format established for these outcomes. That's what a verification witness is. And as I said, it's a standard format, and I hope I can convince you that it is actually being used because it's implemented in a lot of verifiers. Of course, we implemented it, but a lot of other teams implemented it too. And I picked very few of them here. Actually, I talked today earlier to Dirk what his estimation was, how many tools today output such witnesses. And he said it's somehow somewhere between 40 and 50 different tools that already understand and write this format. So now you're probably wondering, what does such a witness look like? What's its structure? How do we use, or what do we use to represent this verification information? What we chose to represent them are automata. And being automata, they of course consist of states and of transitions. And to encode all of this information produced by the verifier, we add some special properties to the states and to the transitions. So our states, of course, can be states without any specific properties, but it can be initial states. So each automaton here has an initial state. It could be a final state, which will be used to represent potential violations. And it could specify invariants, which we can use to convey information about invariants in the program. And we also have special properties for the transitions. And the most important one here would be the source code guards, which will be used to actually map the transitions to the control flow locations and the control flow edges in the program. And the other special property that we have here are so-called state space guards, which are used to restrict the state space. Now I have a short example here with two witnesses. Don't worry, you don't have to understand these witnesses yet. We will come to that later. I just want to use them as examples for the syntax that I just explained. So as you can see, we have the states Q init in both of those witnesses. That are the initial states that I mentioned. We have states without any special properties on the left-hand side, Q1, Q2, Q3. We have final states on the left-hand side. The witness is the one marked in red, the QE1. On the right-hand side, those aren't colored, but those are marked with the two circles as well, are also final states. And you can see the green boxes in the witness on the right-hand side. Those are the invariants. A little bit more difficult to read, probably, are the guards that we have on the transitions. So we have, I can point it out with the laser pointer here, but I will mention it for the Zoom participants. We have between Q init and Q1 on the left-hand side. We have the source code guard that says 3, and the function main. Those are two tokens about the control flow. First of them means it relates to line 3 in the program, and it's supposed to apply when in this line 3 we enter the function main. And then there's a colon. Nothing comes after the colon for this transition, but for the next one between Q1 and Q2. And what you can see there is what I called previously a state space guard, which is used to restrict the state space, such that the witness tells us we should assume that after this transition, n equals 2 in this case. Now there's one special kind of syntax that you might have seen here that I didn't mention yet, the O/W, which we call the otherwise guard. And the otherwise guard is a special kind of source code guard, which basically means that it applies when no other outgoing transition of such a state here applies, right? So that for every control flow edge, we always have a transition that we can go, and by default, that would be this otherwise edge. Right. So now that I showed you, that I gave you a brief understanding what such a witness might look like, let's see what we can use witnesses for, why we think they could be important. So our goals for the verification witnesses in general are that we want to preserve all of that effort that is spent in computing a verification. Because I already mentioned it previously in a different context, software verification takes a lot of resources. It's expensive to do, and it's kind of unsustainable in a way to spend all of those resources to just output some binary answer, yes or no. And it's also unsustainable to output more information than that if you don't do it in a standardized format. Because what happens with proprietary formats is that it goes out of use in a very few years. So after a few years, even if you preserve such some kind of proprietary kind of witness, then it will be of no use. So that is where we can see one of the goals here. Another obvious goal is, of course, you can use them to explain the reasoning that went into the answer that the verifier gave. Explain it in a way that is standardized, because now that we have the standardized format, of course, if I learn it once, then I can understand the reasoning from all of the verifiers that is supported. And more than that, maybe I don't have to look at it manually. Maybe I can use tools that understand the standard format. Which leads me to the next 2 points, facilitating cross-tool information interchange, which we can now use. And the ultimate goal here, fostering the development of some kind of DevOps ecosystem centered around the information reuse regarding software verification, centered around these witnesses, where you can use witnesses for multiple use cases, some of which I will explain in the remainder of my talk. As I already mentioned, the main part of my thesis, and therefore also the main part of my talk here, is centered about the use case of using the witnesses for witness-based result validation. And this use case is I guess, pretty obvious to most of you. So let me still explain it briefly. Here we don't have a verifier, we have a validator. And this validator doesn't take only the verification task as an input, as the verifier did, but it also takes a witness as produced by a verifier as an input. And it takes those 2 components, or 3 if you count program and specification separately, to compute an answer, confirmed or spurious, regarding the verification result that is implied by the witness, right? So the witness might be a violation witness that tells us there was an error. It might be a correctness witness that's supposed to tell you that the program actually models the specification. And now the validator is supposed to tell us whether or not it agrees with this implied verification result using the witness as a guide. And of course, we also implemented this concept, and we even provide during the publications during my PhD thesis 4 different implementations. CPA checker has an implementation, Ultimate Optimizer has one, there's CPA witness to test, and there's F-shell witness to test. And now, as you can see, those are not the only bubbles here. I put another bubble here with those 3 dots because there's other validators out there too that were not developed by us during my PhD thesis, but in some cases even by other teams. So even here, other tools already supported too. Really complicated. It doesn't accept most of my clicks here. Don't know why. Maybe the battery is weak. And the goals here for the witness-based validation, I guess, are also pretty obvious. Of course, we want to increase trust in verification results and improve the reputation of verifiers. And now you might argue, well, okay, then I maybe don't have to trust the verifier, but I still have to trust the validator, right? That's true to some degree. But I can tell you from my own industry experience, and maybe some of you have also made that experience, that it makes a difference in practice to a lot of companies for the adoption of new technology, whether there's an established process of ensuring quality for this technology. And witness-based validation is exactly that quality assurance measure for verification. And the third point on my slide here is no less important than that because it addresses one of the issues that I mentioned in my motivation. Saving developer time. It's the very use case where I said it's very frustrating for a developer to have to spend hours and hours to understand a verification result only to find out that it might be a false alarm. So here, of course, witness-based result validation can also be used to save developer time. Now, one thing probably already bothered most of you when you looked at my previous slide, which is what? It's the binary answer, confirmed and spurious. We didn't want a binary answer for the verifiers. We don't want a binary answer for the validators either. So we also established the concept of so-called witness refinement, which is basically the same thing as for validation, except for one tiny change, namely the output. We don't want the binary answer. We want more information about the process, about the work that went into re-establishing the verification result during the validation. And that's a refined witness. It uses the same format that we use as an input format here. And of course, we also provide multiple implementations of refiners. In this case, one based on CPA checker and one based on Ultimate Optimizer. So it's basically the validator and the validator outputs the refined witness. And that's the refiner. And the goals that we try to achieve with this witness refinement, obviously, are basically similar to the goals that we had for the verification witnesses. Namely, again, we want to preserve this effort. Witness validation is expensive too. So we don't want to go that effort to waste. And of course, we again also want to facilitate the cross-tool information exchange. And we want to enable building new tools, because now you can imagine where previously we might have had verifiers that just output verification witnesses on the one side and validators on the other side that just were able to consume those witnesses. Now we can build tools that consume and output witnesses. And so we can even use those as building blocks to build chains of different tools. And of course, the ultimate goal, again, is what I mentioned on the previous slide of goals as well, facilitating the development of such a DevOps ecosystem, where again, those witness refiners are much more valuable because they have outputs that I can, again, feed into other witness consumers. For example, visualizers. Right? I might want to have a visualizer for witnesses. So why shouldn't I be able to use this visualizer also to understand what the validator did? In this case, the refiner did. So now one thing you might have noticed on the previous figures that we had is I had one figures with validators that had 4 implementations provided by us. And then I had the refiners, which only had 2. Now that, I can assure you, is not to our laziness. So we didn't just give up implementing refiners. That's because there's a conceptual difference across these different validators. So on the one side, we have so-called static validators, CPA checker and ultimate automizer, that we converted into witness refiners. And static validator here means that they basically use static analysis as their technique. So they look at the program source code, but they don't execute the program. On the other side, we have dynamic validators, and they actually execute the program to try and reestablish the verification result. And so let me tell you about how that works. So again, this from the information flow looks pretty similar to what we had before, but there's 2 important differences. One of them you probably already can see. We have the verification task, okay, but now we have specifically only a violation witness, not any kind of witness. And the reason for that is because those dynamic validators will try to establish a bug by example, execute the program to identify the bug by example. And that is, of course, feasible for bugs, but kind of difficult to prove correctness with. Right? Otherwise, we wouldn't need verification. We could just use the tests. And the other restriction we have here that you can't see from the figure is that those dynamic validators require those violation witnesses to be pretty precise. Specifically, they require the violation witnesses to contain concrete variable assignments for each input to a program. And that is the case because they try to extract a test vector. And they use this test vector to synthesize a test harness, which is basically a driver for the program that is to be analyzed, and compile it together with the original program, such that the test harness will feed the test vector into the program. And then when we compile it and execute it, the dynamic validators will observe during the actual execution what happens when the values are fed into the program that was specified in the violation witness. And then, of course, it might find the bug, it might observe the bug when the result is confirmed, or it might not trigger the bug, then the result is again spurious. It just doesn't work. I'm very sorry about that. Yeah. And the goals here for dynamic violation witness-based result validation, among all of the goals that we already saw for witness-based result validation, are that we also have fast validation, usually, because usually executing a program is quicker than statically analyzing it. There are counterexamples you can construct, yes, but usually we have fast validation. However, what's even much more important than that is the outputs that we get from the dynamic validators, because they produce those executable and debuggable test cases. And those have two very large advantages that we can use. First of all, we can use those test cases to communicate the outcome of the verification in the developer's native language. And by native language, of course, I don't mean English or German or something like that. I mean the programming language, and I mean the programming environment that are used and are trained in, because they can just take the test case. They know what a test case is. And that leads to the second point. They can use the test case and even use a debugger to step through the test case and see exactly where things go wrong. And I hope most of you, or at least all of you who have ever written a program and tried to fix a bug and find a bug, will agree with me that it's much more efficient to do when A, can reproduce it reliably, and B, have a debugger to step through it, as opposed to, well, reading the source code and try and guess where the bug is. So that was a lot of theory. So let's look at an example. And as you saw from my previous figures, what we need is not only a program, but we also need a specification. And so in this figure, I have depicted a very simple specification. And for convenience, I use the same language here as for the verification witness because I introduced it already. This is not a verification witness, it's a specification automaton. It just uses the same syntax. And it's pretty simple. It just has two states, S0 and SE. Now it works. S0 and SE. And there's one important transition here, the one from S0 to SE, where SE is our final state, the one that represents the violation. And we can only go this transition according to the source code guard here, if we enter a function called verifier error, right? So our specification says there might be some function verifier error in the program, and if it is ever called, then this specification is violated. So now I have a program here, and it might be a little bit small for you in the back to read it. Don't worry, I have it in a larger size shortly. Actually, just lied. I said it's one program. It's actually two programs. And there's only a tiny difference here. And I pointed out this tiny difference. There's just one variable type that changes. And I tell you that the program on the left-hand side has a bug, and the one on the right-hand side doesn't have that bug. So let me walk you through it by walking you through the buggy version of the program. In this program, we start out with two external function declarations. The first one I don't have to talk about much because I introduced that when I told you about the specification. It's basically what the program will use to encode assertions, the verify error function. The second one might be a little bit more difficult to understand, but actually it's simple. It's just some function, this verify non-net character function, that we use to represent inputs to the program. So you can imagine that this reads some kind of value from the user, from the command line, for example, or would do some system call. For us, as analyzers of this program, what we can assume is that it gives us some non-deterministic value of type unsigned character each time we call it. Now the program starts out in line 4 by immediately using this input function and assigning its value to a variable n. Then there's a simple branching condition where we check whether n is 0, and if it is 0, then we immediately terminate, so we don't have to think about that any longer. And then we initialize 3 variables, v, s, and I, and we initialize all of those variables to 0. Since all of you are experienced developers, you've already guessed that I must be some iteration counter, right? That's true. So we have a while loop here from lines 11 to lines 15, and I is the iteration counter, and n, unsurprisingly, is the number of loop iterations that we want to do. And within this loop, except for incrementing, of course, the iteration counter, we read another input value. In each iteration, another input value, and we assign it to some variable v. And then we add this value v to our variable s. And so what does it do, the program? Well, first of all, it read a number of iterations, and then for each iteration it read a value, and those values are summed up in the variable s, right? So that's what happens here. For the remainder of the program, we just have 2 assertions that are encoded using this verifier error function. And of course, you have to flip the conditions here, right? Because if you go into the condition, then we reach the verifier error function, which means the assertion says that you shouldn't, that the conditions shouldn't be true. So S shouldn't be less than V in line 16, and S should not be larger than 65,025. Why should that be the case? Why should those assertions be correct? Well, first of all, the first one with S should be larger than V should be trivially true, because V is the last variable that we used in the iteration, and we added its value to S. So S should be at least V or larger than that if there are multiple different iterations, right? And the second assertion with this strange large value, I can also explain that. The reason here is that we have at most 255 iterations, and the largest value that we add to S in each iteration is also 255, and 255 squared is this value. So S should never be larger than that. Now, I already said that there's a bug in the program regarding a type of a variable. The issue is variable s here, which is supposed to represent the sum of values. But if it's also of type unsigned character, its maximum value would be 255. So what happens in the C programming language if you try to assign a larger value to it? Well, you have what is commonly called an overflow, or more specifically in this case, it's a wraparound because it's unsigned. And it means that actually what we expected here for the loops, that it would be monotonically increasing value of S, is not guaranteed due to this potential overflow here, to this potential wraparound. And that is how this condition here can actually be violated. And of course, the fix is pretty easy. The fix is simply changing the type of variable s from unsigned character to unsigned integer, because unsigned integer is much larger than the 65,025. So we never get an overflow, we never get a wraparound, and we have this monotonicity. So let me briefly show you a witness. You already may recognize it from before, but now we're actually going into it. We actually now try to understand together what this witness means. This is a violation witness for the buggy version of the program. And it's a witness that could have been produced by some kind of test case generator. So a witness producer that tries to assign concrete variable values to each input function, which, as an aside, would be an ideal witness, of course, again, for the dynamic witness validation, but that's, as I said, just on the side. So we can see here in the transition from Q1 to Q2 that for line 4, the witness tells us to assume the variable assignment n equals 2. That means the witness tells us it wants the program to run with 2 loop iterations, right? So n was a loop iteration limit. So it suggests that we can reproduce a bug within 2 loop iterations. So for each loop iteration, of course, we again get each of the time 1 input value. And the witness again tells us which values we should assume in line 12, both of those loop iterations. First of all, the value 225, and then the value 63. And if you add those 2 values, that of course is larger than 255. So we would get the wraparound, and the value would be 31. And 31 is less than 63. And that is why there's a bug in the program, because that triggers the violation. Of course, I can also show you a correctness witness for the fixed version of the program. Now we have changed the type of variable s to an unsigned integer, and now the program is correct. And I can show you a correctness witness that basically is able to help us prove it. Now, most of the invariants that we can see here are trivial, they are true. But there's one interesting invariant, namely the large box here at state Q2. And the most interesting part of this invariant is the first line, where it says s is less than or equal to I times 255. Now, the location where the witness tells us that this invariant applies is the start of the loop iteration. So at each start of the loop iteration, actually also at the end of each loop iteration, the witness tells us that this invariant holds. And the nice thing is that this invariant is actually an inductive invariant with respect to this loop, which means it is actually preserved, so we can easily prove that it is true. We don't have to take it at face value. We can just use it as a suggestion. The witness tells us we should try this invariant, and we can easily prove it by induction. But it's more valuable than that even, because we can use this invariant and again inductively prove that the two assertions down there are not violated. The second one, of course, trivially, because if the maximum value of I is 255, then of course the value of S will always, according to the invariant that we proved, be lower than 65,025. But from that, it also, of course, follows that it never overflows. And since it never overflows, we have the monotonicity. And since we have the monotonicity, trivially, also the first assertion is true. So we didn't just write down some concepts and some interesting examples. We also tried out our implementations in an experimental evaluation. And what we did here is we took the benchmark set from the competition on software verification. So some of you maybe know this competition, but the important part here is that we have this large standardized set of verification tasks with those 10,521 tasks. What comes on top of that during our extensive evaluation is that we use those tasks and use 2 verifiers to produce witnesses to the best they could for all of those tasks. So we used CPA checker, and we also used Ultimate Automizer to produce witnesses for all of these tasks. To ensure that our results are reproducible and to also ensure the validity of our results, we used the benchmarking framework BenchExec, and we enforced resource constraints that we also documented. 15 minutes of CPU time, for each execution, 15 GB of RAM were available. I also wrote down the concrete machine specification. Now, that's not that interesting right now, but another point on this slide that I would consider to be pretty important here is that all of our artifacts, even though I won't have the time to go into detail for all of those experiments, are available online. They are available in my thesis, but also online. So you can use them, you can check them out, you can read them, and you can try to reproduce them. What I want to show you is just an excerpt of this large evaluation. Namely, for two categories and two types of verification witnesses. First of all, category reach safety. So this is some kind of generic reachability category in the computational software verification, and for violation witnesses. And the way you have to read this table, and the one we will find on the next slide, is you have to see that the header has two lines. The first line in the header of this table will always tell us which tool was used to validate witnesses in the respective columns that it's over. And the second line tells us which tool produced the witnesses that are being analyzed. So here again, we have the results, category reach safety, violation witnesses, and we have 4 validators here, right? The 4 validators that I mentioned previously that are available for violation witness-based result validation. And one thing, of course, to point out is that, of course, even though we have a large amount of verification tasks of 1,809, those are not necessarily all trivial, even for the verifier, which is why the largest amount of results that we get here is 964. So when previously I was a bit harsh and said, well, often we have toy examples. That's not necessarily true all the time. We also have difficult examples in there, right? So what we can see here is we have those 4 validators. We have CPH checker, we have ultimate atomizer, but we also have the dynamic witness validators. And of course, and you would probably already expect, we see that for the dynamic witness-based result validators, the confirmation rates are a little bit slower than for the static ones. Now recall what I said previously when I introduced the dynamic witness-based result validators. I told you that we need very precise witnesses where we have concrete variable assignments for each input function. And of course, that's not always the case for all witnesses. It might still be good witnesses because they can be confirmed using the static validators, but there's some cases, of course, where the dynamic validators will fail. Still, even for the lowest number here, confirmation rate of only, in quotation marks, 37%, when we're taking the witnesses produced by Ultimate Atomizer and analyze it with F-shell witness test. Even in this case, that means that for an absolute number of 184 tasks, you not only have a confirmed verification result that there is a bug, but we also have a concrete test case that can be used by a developer to step through it using a debugger. That's a huge gain of value. On this slide, I have a similar table again. Again, the same category, reach safety, but here for correctness witnesses. Now, the first thing, of course, you notice is we only have 2 validators here. If you recall, it's because of those dynamic validators, they try to confirm witnesses by example, and that's basically infeasible for correctness witnesses. So we only have those static validators here. We have CPA check and ultimate atomizers as the validators here. And here for those correctness witnesses, again, we have oftentimes confirmation rates, 81%, 69%, 98%. The one that stands a little bit out here is the 47% confirmation rate when using the witnesses produced by Ultimate Atomizer to analyze them with a validator based on CPA checker. Now, what I have to tell you here is that the witness-based result validator implemented in CPA checker for correctness witnesses is extremely pedantic regarding the invariance in those witnesses. It will only be able to effectively use invariants that are inductive and imply the safety of the program. So only those invariants are at all relevant to this validator. So that means, in turn, that Ultimate Atomizer produces such great witnesses that in 47% of the cases, you can immediately take those inductive invariants and write them into your C program as assertions to ensure that in the future, you don't have any regressions regarding those invariants. You immediately gain a lot of knowledge about your program. Right. So let me sum up what I told you about today. I told you that we have established a tool-independent, standardized format, machine-readable format for information exchange for verifiers. We have used this format to implement multiple verifiers that can output it, but not only that, we also provided multiple implementations of result-based, of witness-based result validators. And moreover, we not only validate those results, but actually we produce further value. In the one case of those witness refiners, you get a refined witness that tells us a lot, not only about the original verification, but also about what went into the validation. And on the other side, we have those concrete test cases produced by the dynamic witness-based result validators. So in each of those cases, we gain a graspable additional value here. So what I hope is that I was able to convince you that witness-based result validation specifically, but also the whole environment around verification witnesses is useful. It's useful to save valuable developer time, useful to help us understand verification results, to increase trust in verification results, and to increase or improve and boost the confidence that we have in verification technology in general, such that somehow, I hope, I might have made a contribution to make software verification more useful in practice. Thank you for your attention. I will now stop the recording.